Welcome to the second of two videos about the most common types of distortion artifacts in digital audio recordings. These videos presume that you're already familiar with basic principles of digital audio, such as sampling rate, Nyquist frequency, and bit depth. If you're not familiar with these concepts, we recommend that you watch our earlier video introducing the basics of digital audio before watching this one. This series of videos was produced with a particular focus on the needs and interests of biologists who want to work with digital audio recordings of animal sounds. However, the videos mostly cover general principles that aren't in any way specific to recordings of animal sounds. If you're new to digital audio and your interests are in other applications, such as recording music or speech, you might find these useful as well. What do we mean by artifacts? Artifacts are specific types of distortions in a recording that result from errors either in the original recording process or in later manipulation of the digital recording. If you don't recognize these artifacts, you can end up with erroneous descriptions or measurements of sounds. So it's important that you understand how to recognize these artifacts and what they mean for what you can and cannot legitimately do with a recording. In the previous video, we talked about the most common type of distortion artifact in digital audio recordings, namely amplitude clipping. In this video, we'll discuss a less common type of artifact called aliasing, which occurs when a signal that's being sampled contains energy at frequencies higher than 1/2 the sample rate. Aliasing can occur either when a digital recording is first created or when a digital recording is processed to create a new recording with a lower sample rate. Aliasing is much less common than clipping and is usually the result of faulty recording equipment or improper signal processing. To see an example of aliasing, we're going to start out with this synthetic tone sweep, which is recorded at a sample rate of 32 kilohertz, meaning it has a Nyquist frequency of 16 kilohertz. We'll look at aliasing of real animal sounds shortly. Recall from our previous video that the Nyquist frequency is the highest frequency that a digital recording can actually record or represent, and the Nyquist frequency is always equal to 1/2 the digital sampling rate. So let's play this sound, which is a sweep from about 1000 Hertz up to 9000 Hertz. Let's just listen to this. What we're going to do now is to make a new copy of this recording, but at a lower sample rate. We're going to reduce the sample rate of the recording from 32 kilohertz to 8 kilohertz. Because these two sample rates differ by a factor of 4, we can simply retain every fourth sample from the original 32 kilohertz recording, discard all the others, and that will give us a sample rate of 8,000 samples per second, or 8 kilohertz. The process of reducing the sample rate by an integer ratio like this is called decimation. This sample rate reduction was done using an R function called downsample, which is part of a package called tuner for working with audio data in R. When we reduce the sample rate from 32 kilohertz to 8 kilohertz, we'll also be lowering the Nyquist frequency from 16 kilohertz to 4 kilohertz. Let's listen to what the resampled sweep sounds like. All we've done is changed to a lower sample rate. Whoa, that sounds really different from the original. The first 3 seconds or so of that sweep sound the same as they did originally, but the latter part of it sounds really different. Instead of sweeping up in frequency, it sweeps down in frequency, and then it briefly goes up again at the end. To find out what's going on here, let's look at the spectrogram. Here's the spectrogram. We can play this again. You can see that something unexpected happens when the frequency of the sweep rises past the Nyquist frequency of the new recording, or past 4000 Hertz. We know that a recording sampled at 8 kilohertz can't represent sounds above 4 kilohertz. But instead of the sound disappearing, What happens is that where the original tone kept rising, a descending tone appears in the new recording. At any given moment in time, the new aliased tone is below the Nyquist frequency by the same amount as the original tone exceeded the Nyquist frequency, indicated here by delta F. This new aliased downsweep continues down to 0 Hz at the point in time where the original recording exceeds 2 times the new Nyquist, or 8 kHz. It then bounces up again, ending at the same point in time as the original recording. This is a perfect example of aliasing. High-frequency sounds appear at a lower frequency in a new recording at a lower sample rate. To understand what's happening in aliasing, first remember that a digitized signal can only represent frequencies that are less than half the sample rate. Half the sample rate is called the Nyquist frequency. If a signal contains energy at frequencies above the Nyquist frequency of the new recording, the energy at those higher frequency components erroneously appears at frequencies below the Nyquist in the new digitized signal. This is what's called aliasing. Ordinarily, when we make a new digital recording, in order to avoid aliasing, we use a low-pass filter called an anti-aliasing filter that removes frequencies higher than the new Nyquist before the sound is digitized. So why does aliasing even happen? Why, when we're recording a sound at a certain sample rate, would frequencies higher than half the sampling rate show up in the digitized signal at lower frequencies? To understand this, let's go back to the first principles of how digital audio recording works. In this illustration, which we've seen in previous videos, the blue sinusoidal curve represents a pure tone that's sampled many times per cycle at regular intervals. The red dots represent the sample values recorded at a particular sample rate. In this case, the sample rate is adequate to represent the waveform accurately. There are around 12 samples in each cycle of the sound wave. Recall that one cycle is the time from one peak or trough to the next one. Remember that a digital audio recording is simply a sequence of numbers giving the heights or sample values of these red dots. Although some of the red dots are not exactly on the curve, they're close enough that you can easily reconstruct this sound wave from them later on. What happens if we take this same sine wave and sample it at a lower rate? Let's take a look at what that might look like. In this illustration, the blue curve is exactly the same as it is in the first panel. But now the sample rate is much lower. The interval from one sample to the next, which is labeled delta t here, is longer. In fact, there are fewer than 2 samples in a single cycle of the waveform. In other words, the sample rate is less than 2 times the frequency of the tone represented here. Remember that when we save a digital audio recording, all we're saving is the sample values. We don't have that continuous curve. We just have the sample values, the heights of those red dots, along with information about how frequently those red dots were sampled. So we have times and we have sample values, which are proportional to sound pressure at those times. So we throw away the blue curve, leaving just the sample values at these relatively infrequent times. Later, we're going to treat this series of sample values as a representation of a continuous sound pressure wave. We may play it through our computer speakers, or we might subject the digital representation to some kind of analysis, like making a spectrogram to let us see what frequencies are present there. What happens when we go to reconstruct the audio recording from these sparse sample points? Well, that's what's shown here in the red curve. What we've done here is we've just taken the sample points and we've fitted a sine wave to them. And the red curve is the closest sine wave we can get that fits those few points as well as possible. But notice that when we compare the red reconstructed wave to the blue original wave, which was an accurate representation of the frequency of the sound, the periods of the reconstructed wave are longer. In other words, that reconstructed sound wave is lower in frequency than the original. So because of this inadequate sample rate, these high-frequency sounds get misrepresented or erroneously recorded at lower frequencies. That's what aliasing is. Let's take a look now at aliasing in some recordings of real animal sounds. To start, let's look at this recording of a bearded seal singing its territorial song in the Arctic waters off of Point Barrow, Alaska in April. This recording was originally made at a sample rate of about 11,000 hertz, giving it a Nyquist frequency of about 5,500 hertz. The spectrogram here doesn't show quite all of that frequency range. The song is a descending tonal trill, which starts up at around 4,000 hertz and sweeps down rapidly to about 1,000 hertz over the course of the first 7 seconds of the song, and then continues to go down slowly after that. Let's listen to what this sounds like. Now let's take this recording and resample it to reduce its sample rate to 1/5 of the original, from 11,000 hertz to about 2,200 hertz. That means the new recording will have a Nyquist frequency of about 1,100 hertz, and that's shown by the red line in the top spectrogram. Look particularly in the new resampled recording at what's going on in the first 11 or 12 seconds, and compare that to what you see in that same time interval in the original recording. You can see that the recording is aliased. The portion of the original recording that was above the new Nyquist frequency is folded over. It's like a vertical reflection around the Nyquist frequency shown by the red line in the top spectrogram. During that part at the start of the recording, what was originally a downsweeping trill is now an upsweeping trill. The shape of the call is upside down or inverted up until the moment when the song in the original sweeps down below the new Nyquist. After that point, it all looks normal. Let's see what that sounds like. If you were to encounter this recording and you didn't already know what the songs of bearded seals sounded like, you might think this is what they're like. They start between 800 and 1,000 hertz, sweep rapidly down over around 1 second, then sweep up over a course of 5 seconds or so, up to about 1,000 hertz, and then they slowly sweep down again to around 200 hertz over 40 seconds or so. And in fact, that description of the song would be completely mistaken. If you didn't realize that this recording was aliased, you wouldn't know that it misrepresents what the song actually looks and sounds like. What would this new recording at the reduced sample rate look like if it were created properly, without aliasing? This recording has the same sample rate as the second one, but before reducing the sample rate from 11,000 to a little over 2,000 hertz, we applied a digital anti-aliasing filter in software to filter out or remove frequencies above the new Nyquist. Let's listen to this. In the first 10 or 11 seconds of the recording, there's no sound from the seal at all. There's just the quiet background noise of the Arctic Ocean. At around 12 seconds in, we begin to hear the descending trill as that trill comes down below the Nyquist frequency of the new recording. Let's look now at an example of aliasing due to a faulty recording system. This is a recording of a Socorro mockingbird in Mexico. Let's listen to this. One important thing to know about this recording is that it was not made with a device designed primarily for recording high-quality audio. This is actually the audio track of a video captured by this digital camera. Let's listen to this again. Pay close attention to the sound of these last 3 notes of the song. Those last 3 notes have an odd buzzy quality to them. If we look closely at the spectrogram, we could see that in fact these notes are significantly aliased. Each of these last 3 loud notes sweeps down from a little over 4,000 Hz to around 2,000 Hz. But superimposed on them are these inverted elements that sweep up at the same time at a series of varying frequencies up above the original sound. Let's slow this down to 1/4 speed and see if we can hear that, especially in those last 3 notes. Those last 3 notes sound kind of buzzy. They're audibly distorted in some way. It's hard to hear this at the normal speed because the bird sings quite rapidly. But at the slower speed, you can hear that they sound kind of odd. So what's going on here? Why are we seeing aliasing in this recording? Digital audio recording devices always contain built-in hardware anti-aliasing filters to filter out sound energy above the Nyquist frequency before digitizing a sound. But anti-aliasing filters are not all created equal. Some are better than others. High-quality digital audio recording devices will have high-quality filters that do a good job at removing energy above the Nyquist frequency. Lower-quality recorders may have filters that remove some of that high-frequency energy, but not all of it, allowing some aliasing to occur. Recall that in this case, the device that made the recording is not designed to be primarily an audio recorder. It's a camera. Although it's a very good still camera, it's not a very good audio recorder. And we can see here one of the reasons why it's not very good as an audio recorder. It has poor anti-aliasing filters, and recordings made with this camera are prone to aliasing. Where did that high-frequency energy that got aliased come from in the first place? One possibility is that the bird's song actually contained harmonics that were above the Nyquist frequency of 24 kHz. Another possibility is that those higher harmonics were themselves the product of other types of distortion elsewhere in the audio recording system of the camera. Without better recordings of the bird's song for comparison or deeper investigation of the camera's audio recording system, it's impossible to tell. In any case, if your recordings are made with high-quality dedicated audio recording devices, it's very unlikely that you would encounter aliasing like this because the built-in anti-aliasing filters would prevent this. So one way that aliasing can occur is as a result of faulty recording equipment. Let's look now at an example of aliasing of a real animal sound as a result of improper signal processing. This is a recording of a bird called the dusky-capped flycatcher. Let's listen to this. A researcher who was studying these birds had collected recordings from several different sources, and among the recordings, there were 2 different sample rates. Some of them were sampled at 48 kHz, and some were sampled at 22.05 kHz. Because this person wanted to compare measurements from spectrograms across all these recordings, they needed to get all the recordings converted to a single common sample rate. So they decided to downsample the recordings that were originally made at 48 kHz to a sample rate of 22.05 kHz so that all the recordings would be comparable. They did a little Googling around to look for ways to convert sampling rates of audio recordings and discovered a function called downsample in the R package tuner. So they used this package to create new recordings with a sample rate of 22.05 kilohertz from the original 48 kilohertz recordings. And this is what they got. Let's listen to it. It sounds pretty similar, but subtly different. But when we look at the spectrogram, it looks really odd. Each song element that's shown in the original recording on the top is clearly visible in the bottom recording, but for each element there are multiple vertically inverted copies, upside down from the original, that are superimposed on the original spectrographic image. This is very similar to what we saw in the recording of the Socorro Mockingbird earlier that was a result of faulty recording equipment, and it's a classic illustration of aliasing. The problem in this case is that there was no filtering of the original recording prior to the resampling, and that gave rise to aliasing. Let's see if we can hear the difference more clearly. What I'm going to do is play just this first element of the recording at 1/4 speed. First in the original 48 kilohertz recording, and then in the downsampled aliased recording. So, first in the original, and now in the aliased downsampled recording. You can hear that there's a slightly fuzzy or buzzy sound to the downsampled version, which is a result of the aliasing. Let's just review briefly the way aliasing appears in spectrograms and how you can recognize it in a recording. The first thing to bear in mind is that aliasing can only be detected in spectrograms, not in waveforms. There's no consistent visible pattern in waveforms that would tell you that a recording is aliased. There are two fairly common ways that aliasing may be visible in a spectrogram. First, if the sound in your recording includes a frequency sweep either up to or down from the Nyquist frequency, it appears in the spectrogram to bounce or reflect off of the Nyquist frequency, visible in Raven Pro spectrograms as the bottom edge of the gray background area in the spectrogram. In the case of a frequency sweep, the portion that gets folded over from frequencies greater than the Nyquist occurs at a different time from the unaliased portion of the signal that are below the new Nyquist. The second common way that aliasing appears in spectrograms is as vertically inverted replicas or duplicates of a signal overlapping the original spectrogram image and synchronized in time. These are calls of a tropical bird called a screaming pia. You can see that most of the signal's energy is below 6,000 Hz, and above it you see multiple copies of that spectrographic signature that are inverted and synchronized in time. This again is a classic case of aliasing. In this particular case, this also was a result of equipment failure in the recording device that originally made this recording. What can you do with aliased recordings, and what can't you do? First of all, it's important to understand that aliasing cannot be fixed or undone. If you have a recording that was aliased when it was first created as a digital recording, there's nothing you can do to fix it. If you have an aliased recording that resulted from resampling an earlier non-aliased recording, you can go back and repeat the resampling procedure after applying an appropriate anti-aliasing filter in software. Aliasing, like clipping, corrupts the spectral structure of a sound. So, as with clipping, that means that frequency-based measurements, such as peak or center frequency, bandwidth, and so on, are unreliable for aliased signals. On the other hand, time-based measurements, for example, durations of sounds made from spectrograms, are unaffected by aliasing. If your main interest in working with recordings is to identify or count particular sounds, often you can do that just fine with aliased recordings as long as you can still recognize the types of sounds that you're looking for in the spectrogram. That wraps up our look at digital audio artifacts. Thanks for watching.